Hello everyone. Welcome to the sessions on the advanced communication. This is the session 4 in the unit 1, that is the microwave devices. In this particular session, we are going to learn about the two cavity Klystron tube. The contents which we are going to cover: two cavity Klystron tube construction, working, and the application of that particular two cavity Klystron. Now, basically, this two cavity Klystron, it is nothing but the microwave amplifier here. Microwave amplifier. As we know, amplifier is a circuit which takes the input as the small strength signal and provides the output as the large strength signal. Means it will boost the energy. It will increase the energy of the signal here. In the same fashion, since the conventional transistor and all we cannot use in the microwave frequency range, we are having the special devices to operate at the microwave frequencies. That is one of the devices, the two cavity Klystron. It is an amplifier circuit. Means it is acting as the amplifier for the microwave frequencies here. Now the construction wise, if you observe here, the construction, it is having the two cavities. First one is, this is the buncher cavity and this is the catcher cavity. Two cavities are present, buncher cavity and the catcher cavity here. And in case of the buncher cavity, we are applying the input here. Input which we want to amplify, that is applied to the buncher cavity, and finally output is taken from the catcher cavity here. Finally the output is taken from the catcher cavity. Now here if you consider at this end, the particular that is the cathode will be present, or the electron gun which will generate the electron. With the cathode or the electron gun will be there, which is generating the electron beam, very high velocity electron beam. And this is the collector point, which is at very high positive energy compared to this collector, which is at very high positive energy compared to this collector here. And also we are having two electrodes, that is called as the focusing electrodes. These are the two focusing electrodes, and which are a little bit positive voltage compared to the cathode, but less than this collector. The main purpose of this focusing electrode is to focus the electron beam towards this collector such that they will not disperse. They will not disperse. Those should be directed towards this particular collector. For that purpose, this is the focusing electrodes here. Now the cathode, this tube or the electron gun, it is generating the electron beams here. Now this space between this buncher cavity and the catcher cavity, it is called as the drift space here. This is called as the drift space, and here it is the gap A. This is the gap A, and this is the gap B here. This is the gap B, gap A. This is the drift space here, correct? And the bunching will take place in the drift space here. The bunching will take place in the drift space. Now, if you just move on to the working principle, how actually it works here. From the electron beam or electron gun, the electron beam is generated. They will start moving with very high velocity. They will move towards the collector. They will move towards the collector. If there is no input in the buncher cavity, then what will happen? With their own velocity, the electron beam will travel here. With their own velocity, the electron beam will travel and they will reach this collector here. But if you apply the input signal, then what will happen? Once the input is applied here, at this particular input cavity or the buncher cavity, like this, the input signal is applied, means this field, input RF field will be there, no? That will affect the velocity of the electrons here, because it is positive cycle, negative cycle, like this. Whenever the positive cycle comes here, electrons will be accelerated here. And whenever the negative cycle comes here, the electron speed will be reduced there. Therefore, in the absence of the particular the RF signal or the input signal, the electrons will move with their own velocity. But once the input is applied, the electron velocity will be modulated here. That will be modulated here. Now we will analyze that one using the apple gate diagram. Now see here the same diagram here. This is the collector which is at more positive voltage compared to this electron gun here. Correct? These polarities you can see. This is the drift space here. This is the buncher cavity. Correct? This is the catcher cavity here where the output we have taken, and here the input is applied here. And this is the drift space where the bunching of the electron will takes place here. Now the how the bunching of the electron is taking place, how the electrons will can collect one another, or they can move with the same velocity, because the electrons which is generated first, that will move here. For example, if you consider here, one electron will be there x, one more is there y, and one more electron z here. Suppose the electron x is generated first, means it will move first here. X first comes first here, and one more electron y which is generated afterwards, means it will comes afterwards. After some time the y reaches, and z means after some time the z will reaches there. Then how the bunching is taking place here, how the all the three electrons are carrying with each other. Correct? How they are making one bunch here. Then how that process is happening here, that we can understand through the Applegate diagram. Now observe here, we are having three electrons here. One is the electron x, one is the electron y, and another is the electron z here. Another is the electron z. This is the x electron position, this is the y electron, and this is the z here. Correct? Now the electron y is there when the particular input RF signal is 0. When the RF signal is 0, then the electron y is coming, and the electron x is coming when the input RF signal is negative. Similarly, electron z is coming when the input RF signal is positive here. This is 0, this is negative, and this is positive here. Therefore, three electrons are coming at a different time intervals here. One is at positive, one is at negative, and the one is at the 0 level. Now what will happen, that is x, y, and z. If you consider here y, and one more is x, and one more is z here. Correct? That is x, y, and z. If you consider here, suppose this is the electron x, this is the electron y, and this is the electron z. Or you can analyze using one example here. For example, you consider x, three persons are there, x, y, and z. There are three persons, x, y, and z. Now x, he is leaving he want to reach some place there. Suppose this is the one place, all of them, x, y, and z, all of them want to reach here to this particular point here. Right? All of them want to reach here. Now the x, the person x, he is leaving the spot at 10 o'clock, 10 a.m. At 10 o'clock he is leaving, but he is walking. He is going by walk here. Correct? He is going by walk. Now the y leaves the place at 10 here. After 10 minutes he is leaving. But he will go with the bicycle. For example, he is moving with the bicycle here. Now one more person z, he leaves the spot at 10:20. At 10:20 here. But he moves with the two-wheeler here. Bike. Two-wheeler. Now what will happen? Even though x is leaving this place at around 10 o'clock, but he is walking, moving by walk here. Correct? He is moving by walk. Now y is leaving the space at 10:10, but he is going with bicycle. Now z is leaving at 10:20, even though after 20 minutes from the x, but he is going by two-wheeler here. Then what will happen? At some point here, all of them can catch up with each other. All will meet here, because even though x is leaving earlier, and after that y is going, and after that z is going, but their journey is different here. This person is going by walk, this person is going by bicycle, and this person is going by two-wheeler here. Therefore, their mode of journey is different. Therefore, there is a possibility that at some point all of them will meet here. Therefore, all of them will meet, and when all of them will meet, they form the bunch here. They form the bunch, and during this bunching process, the higher velocity electrons will give their energy to the lower velocity electrons, and they will move with one average velocity. They will move with them average velocity. In the same fashion here, if you consider here x, it is retarded here. Even though x is emerging out first only, but it is retarded. Its speed has reduced here because the negative signal is there at the input. Negative signal is there at the input. Similarly, y is coming after x, but at that time the input is 0. At that time the input is 0. Therefore, it is moving with the same speed here. Now the jet is coming afterwards here, after some time, but it is accelerated because positive energy is there at the input cycle there. Therefore, it is accelerated. It will move with very high velocity. Therefore, at some point, all of them will make a bunch here. The bunching will take place, and for one cycle, one bunch will be formed here. For one RF cycle, one bunch will be formed. Now, in this way, the bunching of the electrons will take place, and the higher moving electrons with the highest speed electrons, they will give their energy to the lowest speed electrons, and they will move with one average velocity there. Therefore, this form the bunching, and in this bunching process, the current modulation will take place because of this high energy. The current modulation will take place, and they will give out their energy to the field here. Therefore, the particular uh, amplification is taking place. That is, if you observe here, the energy is applied here, the bunching of the electron is taking place. Once they will reach here, that bunch of energy is applied to this output tube here or the cavity. Now this output cavity is also oscillating same as the input here. The frequency will be same, but with much higher energy, because all the bunches are together here. Electron bunches, they are providing their energy here. Therefore, the output will be of much higher signal. Suppose this is the input signal here, which we have applied here, means here output will be of much higher. That is like this, you will get here the oscillations will be of much higher strength. Those are amplified. Those are amplified. This is called as the two cavity Klystron tube. Explanation with respect to the Applegate diagram here. Now again here, see here, this is the reference electron TB, which is moving with the same speed. But the one which is coming earlier, TA, it is moving slowly. Why? Because it is having the retardation there. It is having the retardation. Similarly, one which who is coming afterwards, after B electron, then it is moves very fast. Why? Because it is having the acceleration. High positive energy will be there at the input. Therefore, all the three will move, and at some point they will catch up with each other, and the bunching process will take place there. Therefore, the bunching process will take place, and the high velocity electrons will give up their energy to the lower velocity electrons, and in this way, particular amplification of the signal will take place there. Now the operation here, how it is operating, there are mainly three things are happening. One is the velocity modulation, second is the bunching, and third is the current density modulation. Because velocity modulation means what? Without any input signal, all the x, y, z, all will move with the same velocity, with their own velocity, and they will reach one after the other. First will reach x, afterwards y, afterwards z. But here the velocity modulation taking place. Why? Because the input RF is applied depending on the polarity of the RF signal, the velocity will be increases or reduces. Therefore, the modulation of the velocity is taking place. And the second process is the bunching. Once at some point in the drift space, all the three electrons will meet and the bunching will take place. And the high velocity electrons will give up their energy to the low velocity electrons. And in this way, the bunching process completes there. And they will give up their energy to the catcher cavity there, which is oscillating as the same as the buncher cavity. Now the current density modulation, because the current is now strength is increasing there, therefore the density modulation is also occurring. Now the performance of this two cavity klystron. First one is the frequency range. It will use operate at the 250 megahertz to 95 gigahertz. Power available is much higher than the currently needed. That is, it is generating much higher power which we need currently. And the gain of Klystron is at UHF is 30 to 35 dB. Ultra high frequency level it is 30 to 35 dB. And at microwave frequencies it is 60 to 65 dB here. Applications, that is UHF TV transmitter. In case of the TV transmitter, this two cavity Klystron amplifier is used. In the long range radar pulsed, this is also used. And in the linear practical accelerator, pulsed accelerator also this amplifier is used there. And in the earth station of the transmitter, in case of the satellite applications, in the earth station also the particular two cavity Klystron amplifier is used there. Now let us watch one small video such that we will get the clarification about the working of this two cavity Klystron amplifier.
To generate and to amplify radio waves with very high frequencies, so-called microwaves, special tubes are required. For example, the Klystron. Consider a simple Klystron amplifier. The essentials of this simple Klystron are the electron beam, and two metal boxes known as cavity resonators. The cavity resonators have a potential which is positive with respect to the cathode. Thus, the electrons emitted by the cathode are accelerated towards the first resonator. Because the resonators have apertures in the form of grids, the electrons will continue until they reach the collector, which is at the same potential as the resonators. Therefore, in the region between the first resonator and the collector, the electrons would have a constant speed if it were not for the influence of the cavity resonators. In reality, the first cavity resonator is supplied with the weak high-frequency signal which is to be amplified. This signal will initiate an electromagnetic field inside the cavity. Due to this field, the velocities of the electrons passing through the first resonator are modulated. On arriving at the second resonator, the electrons will induce there another electromagnetic field of the same frequency. This field is so strong that it is possible to extract a large signal from the second cavity. To understand this amplification process, it is necessary to study the behavior of a cavity resonator in detail. There is a certain similarity between a cavity resonator and a conventional resonant circuit. A simple resonant circuit consists of a capacitor and an inductive loop. It is known that a conductor contains free electrons. Charging the capacitor to obtain a voltage of this polarity means that many electrons are removed from the upper plate and an equal number of electrons are introduced into the lower plate. Thus, there are two charged layers. One layer has an excess of electrons and is therefore negatively charged. The other layer has a shortage of electrons, which reveals itself as a positive charge. the electric field lines are directed away from the positive charge. If the capacitor is charged with the reverse polarity, the direction of the field lines is also reversed. The displacement of electrons in the loop constitutes an alternating electron current, which is symbolized by the variations of the green arrow. The alternating current gives rise to an alternating magnetic field. The magnetic field of the loop is out of phase with the electric field of the capacitor. At the moment that the magnetic field is at maximum strength, the electric field is zero. A quarter of a cycle later, when the electric field is at maximum strength, the magnetic field is zero. There are two similar situations in one cycle at which the fields have the reverse direction. Thus, the oscillation which was started by loading the capacitor represents a certain amount of energy that is continuously exchanged between the electric field and the magnetic field. The smaller the value of the capacitor and the inductivity of the loop, the higher the frequency of the oscillation, or the resonant frequency. With this simple circuit, a rather high frequency can be obtained, because the inductance of a single loop is very small. To obtain higher frequencies still, the inductance can be further reduced by placing two or more loops in parallel. This results finally in the formation of a closed resonator having certain very high resonant frequencies, which are determined by the dimensions and shape of the cavity. In a closed resonator, the magnetic field, as well as the electric field, is confined to the interior of the cavity. The associated currents and charges are to be found in a thin layer of the interior surface of the resonator. The first resonator of the klystron is excited by the external signal which is to be amplified. This signal, often introduced via a coaxial cable, must have a frequency at which the cavity can resonate. The current in the coaxial cable sets up a magnetic field, which in turn brings the resonator into operation. That is to say, that also an electric field is originated. It is sufficient to consider only the electric field in order to understand the modulation of the electron beam entering this first cavity resonator. The electric field lines indicate the direction of the force acting on a positive charge. The electrons, being negatively charged particles, will therefore be accelerated if they move against the direction of the electric field. On the other hand, the electrons will be decelerated if they move in the same direction as the electric field. With the alternating electric field present, the electrons will thus be alternately accelerated and decelerated. Consequently, they will enter the field-free space between the two resonators at varying speeds. In this space, known as the drift space, the fast electrons will overtake the slow ones and bunches will be formed. The second resonator is located in the position where the bunches contain the greatest number of electrons. The bunches arrive at the second resonator at intervals corresponding to the frequency with which the first resonator oscillates. As both cavities are made identical, these intervals also correspond to a resonant frequency of the second cavity. Therefore, the latter starts to oscillate. The alternating magnetic field inside the second cavity is partly linked with the coaxial cable and thus initiates the output signal. Summing up the whole action of the klystron, the electrons coming from the cathode enter the first resonator with high kinetic energy. This first resonator is set into oscillation by the input signal so that the beam is modulated and bunches are formed in the drift space. These bunches, in turn, set up an electromagnetic field of the same frequency in the second resonator. From this field we can extract a larger output signal. We must now consider why the output signal is larger than the input signal. A constant stream of electrons enters the first resonator so that almost equal numbers will be accelerated and decelerated. Thus, the average kinetic energy of the outgoing electrons is nearly equal to the energy of the incoming electrons, and almost no energy is taken from the field of the cavity. At the second resonator, however, the majority of the electrons are in bunches, and these are decelerated. Only very few electrons are accelerated. The result is that almost all the kinetic energy is converted into electromagnetic energy. The electromagnetic energy of the field which produces the output signals. amplification of such a two-cavity klystron is too low, then multi-cavity klystrons may be used.
Okay, students. Now this completes the working of the two cavity Klystron amplifier. That is actually how it works. What is the constructional diagram of the two cavity Klystron and what is the Applegate diagram. Using that we have analyzed how actually the bunching of the electron is taking place there, how the each electrons are catching up with each other and when they are moving with the average velocity, and when the electron bunches are decelerated, that is when their velocity reduces, then they will give their energy to the field. If those are accelerated means they will take energy from the field there. Therefore whenever they are retarded, when their energy reduces, they will give their energy to the field there. In this way the particular amplification process is taking place here. In the next session or in the next class, we'll start up with the one more device of the microwave signals. Thank you for watching. Thank you.